Good morning, everybody. Welcome to this morning's session. Max Schmidt deeply appreciates your attempt to arrive here on time, and we all are looking forward to an interesting session this morning on metamorphic and magmatic processes at high pressure. Just in case you don't know, this is, in fact, a session that's been scheduled as part of the honorifics due to Max Schmidt for his reception of the Dana Medal from the Mineralogical Society of America. And all the talks that we'll be seeing are, in one way or another, related to some of the contributions that Max has made over his short but excellent career. The first talk this morning is entitled The Solubility of Niobium-Bearing Rutile in Aqueous Fluids Containing Albite, Sodium Chloride, and Sodium Fluoride from 1 to 5 GPa and 300 to 600 degrees C. The authors are Tanis, Simon, Schauner, Chow, Xiao, Hanchar, Shen, and Zhao. I hope I don't have to do that a bunch of times. There are two talks here. Is it the later one?
Yeah.
This will go off at 11, and then the red will start, the yellow will be at 11, and the red will be at 13.
Okay, I think that's okay.
Just that.
Thank you.
Height.
So again, I just want to thank my collaborators with UNLV and HIPSEC. The Advanced Photon Source, the beamline scientists, have been really helpful with us, and John Hanchar from Memorial University. So what was motivating our experiments in this project was to really understand the role of aqueous fluid at moderating trace element mobility. During subduction of the oceanic plate, we get a large amount of dehydration, which releases water into the mantle here. And a number of studies have shown that it's not a pure water phase, but it has some sort of dissolved component. And this dissolved component can have an effect on the solubility of various minerals. And one of the minerals that is of importance to us is rutile. It's considered to be stable during the subduction process, and it's also a host phase for niobium and tantalum, the high field strength elements. And if we look at the geochemistry of rocks from arc settings, we see a depletion in niobium and tantalum. And that depletion varies from arc to arc. And what also varies from arc to arc is the pressure and the temperature in which the fluid is released. And so over the years, a number of studies have been done, and here I show a nice compilation of experiments and previous work from Rapp et al. In 2010. And what she showed is that if you add some dissolved component NaCl or NaF into the fluid, you get an increase in the titanium solubility. And so here she shows, as a function of temperature, titanium solubility. She uses work from Troper and Manning, Odetet and Kepler, and Antignano and Manning. And so here she starts with pure water, and they see that solubility increases with temperature. And if you add an albite component, the concentration also increases in order of magnitude. And in her experiments, she added NaCl, which also increases solubility, and then finally NaF component, which increases solubility the most. And we see that there is a large range of pressures in which these experiments were performed, from 700 to 1100 degrees C. But the range of pressures is only from 0.5 to about 2 GPa. And so if we look at a plot of pressure versus temperature with the current experimental data, we see that all of the data plot in this high temperature range and is extrapolated to cold and hot subductions, which I've plotted also on this plot adapted from Hacker. And so really, this lower to moderate temperature, high pressure range is unconstrained. And so what we really hope to do is use a diamond anvil cell technique to achieve higher pressures and to start contributing to a data set in this range. And to do that, we used an in situ synchrotron X-ray fluorescence technique. And we started by achieving high pressures and high temperatures using a hydrothermal diamond anvil cell, shown here. It's resistively heated. Inside our diamond anvil cell, we have a rhenium gasket, which is lined with gold. The gold acts as an inert barrier for if we're using some fluid that is a HCl fluid or NaF fluid. It also acts as our way to determine pressure using X-ray diffraction of the gold. We place a niobium-bearing rutile crystal, and then we also place our desired fluid inside our sample chamber. And if we're doing experiments with albite, we add an albite crystal. And so at the synchrotron, our incident energy is 27 keV. The excitation energy of niobium is 16 keV. And so we used a niobium-doped rutile crystal because we can see the niobium K-alpha where we cannot see the titanium K-alpha. And we assume congruent dissolution and calculate our titanium concentrations. So once we have our cell loaded with our sample and our crystal, we place it on an X-ray beamline shown here. Here's our X-ray detector. We also have a microscope where we can look at our sample chamber during heating and at various points during experiments. So after we are to heat up our cell, we can rotate the cell in the direction of the X-rays and then use the X-rays to excite the niobium in our sample chamber, which is detected in a backscattering direction with our X-ray fluorescence detector. So this is an example of the X-ray fluorescence spectra. On the bottom we have energy, and here we have normalized intensity, and here is the niobium peak. Before we can determine what the concentrations are at high pressures and high temperatures, we need to do a standard calibration. And to do the standard calibration, we load known amounts, known concentrations of niobium fluid into our diamond anvil cell and do X-ray fluorescence experiments. And so here we have 1,000 ppm and 300 ppm. We normalize the spectra to the beam intensity and to the time. And if we integrate the area and plot it versus concentration, we get a nice linear relationship, which has also been shown previously in the literature. We also do put the cell on empty to ensure that none of the components can contain niobium, and so this 0 point is a true 0 point. So once we have a good standard calibration, then we can load our high pressure, our crystal, and go to high pressures and high temperatures, and then we can plot those concentrations along our calibration curve to determine the concentration. So in 2010, Deleuze and Manning published a really nice thermodynamic study where they predicted the solubility of rutile in pure water. And what they found is that as density increases, the concentration increases, and as temperature increases, the concentration also increases. And so we felt that density is a nice way to incorporate pressure and temperature. And so this is how I'm going to be presenting the data. And so, as I mentioned, they calculated a predicted solubility, and when they plotted the current experimental data on pure water, in that temperature and pressure range, it matched up quite nicely. So when we start to make the fluid more complex, as shown here, we add an NaCl component as RAP did in 2010, and we see her data at 0.5 GPa and 800 degrees C has an increase in the concentration relative to pure water. Our data are from 300 to 500 degrees C. We use two different concentrations, 10% and 20% NaCl, and we are at much higher pressures from 2 to about 5 GPa, and we also see an increase in the concentration relative to pure water. If we add an albite component, as was done previously at lower pressures and higher temperatures, they also saw an increase in the concentration relative to water, and we also see an increase in a concentration relative to pure water at lower temperatures and higher pressures. So in these cases, the albite component is less than 10%, and so we have over 90% water, and so the densities are calculated with pure water. And most recently, Hayden did a study where they looked at a supercritical albite fluid, and they had, on average, 50% albite in their system. And it was supercritical, so it was one fluid, so it was only proper to take into consideration the density of the albite. And so even though she is at much lower pressures, 1 to 2.2 GPa and 900 degrees C, the density is much higher because it is a supercritical albite fluid. But we still see the trend where when you have a more complex fluid, we have an increase in the concentration. And finally, we looked at a NaF solution as RAP in 2010 did, and here we see that her concentration increased the most relative to pure water, and in our case, at higher pressures and lower and moderate temperatures, we get on the order of adding an albite component. And so from the work that we've done, we've confirmed that if you add a dissolved component, you get an increase in the solubility of rutile. What we've also shown is that the solubility of rutile in a dense fluid is comparable and actually it exceeds that of less dense fluids. And so we've covered a much larger pressure and temperature range, which is a complement to the previous work. And what we still want to understand is what is really driving this enhanced solubility. Is it pressure and or temperature, a combination of the density, or a complexation with the dissolved components in the fluid? So again, thank you to my collaborators. And any questions?
Questions? It's very hard to see people
Yeah.
here, so. Yeah, Peter.
I'm curious, have you gotten to the stage yet where you're willing to hold your nose and look at experiments where people have done partitioning between fluids and rocks, like a whole periodic table? See how it's data compare?
So we have started to do that, but not in great detail.
Because, I mean, the question we have to ask ourselves is, what are the dissolved components?
Right, it's a big issue.
More questions?
There's one, I think, over there.
Go ahead.
I'm curious why you chose Albite instead of J-Gas, since you're at a high pressure. I mean, I'm not suggesting it's going to make anything different, but normally, like, equilibrium things that are approaching equilibrium, Craig has shown that J-Gas is really not.
That's a really good point, and it could be something that we could consider in the future, but we wanted to compare our results with the current published results. So we chose Albite because that's what has been done previously.
Everybody should have done J.
Yes.
Any other questions? One last question. If not, let's thank you very much.
Thank you very much.
And let's move on to the next talk, which is entitled Crystallization of Oxidized Moderately Hydrous Arc Basalt at Mid to Lower Crustal Pressures. The speakers are D. Blatter, T. Sisson, and W. Hankins. Originally scheduled to give the talk was Blatter, but I guess she's under the weather, so Tom is going to...
Right, so Danica called me for all of you who came to see Danica, you're going to be disappointed. She called me at 5 this morning. She has the flu, vomiting and worse. So she emailed me these slides, and I've seen them once at 6 this morning. But I know the project pretty well, so please bear with me. I'm just going to stumble through this, and if I look a little blank when they come up, bear with me. So what we were interested in is production of calc-alkaline andesites. A lot of you in the room are interested in that problem. You probably all know the history. Many people have conducted experiments at both atmospheric pressure and at low pressure, including myself. One of the findings quite some time ago now was that the addition of water to the system facilitates the production of calc-alkaline liquids. But some of the water concentration, well, we know a lot more about the water concentrations of natural arc magmas than we did 20 years ago. And so I wanted to reinvestigate that problem. And then also there's a notable lack of information on the crystallization behavior of basalts in deep crustal conditions. So I guess that's the motivation. The conceptual model I think that a lot of us have is that basalts, of course, they get generated in the mantle wedge, and then they run into the crust and they stall somewhere in the deep crust, probably due to density, and they undergo crystallization differentiation down there. They may also melt the crust and assimilate material from the crust. That's the fundamental problem that we were trying to investigate. So we did a series of piston cylinder experiments. We used a basalt that's typical of the basalts that are near Mount Rainier. It's relatively high magnesium. It's not as magnesium as what you may find something else that you like more. But this is typical of the kinds of arc basalts that erupt around Mount Rainier, which is where I'm paid to work. We synthesized that basalt with 3% water added to it. The way we did that is to fuse this to a glass with a high water concentration in it, and then mix that with the dry starting material, fuse that to a glass, check the water concentration with FTIR, and then basically iterate until we had 3% water. The way we do things in this lab, we always end up with about 1,000 parts per million CO2, which can be a disadvantage or it can be a virtue. We did them runs in piston cylinders at 9, 7, and 4 kilobars. We buffer them. Everything we do in the USGS lab, we buffer, because we can do this because we have 1-inch assemblies that I inherited from Steve Bolin. So we use a double capsule method. In the outer capsule, we use rhenium and rhenium oxide. And we don't put pure water in the outer capsule. We put a mixture of H2O and CO2 that's tailored to match the water fugacity that we would expect for the sample in there. And we use rhenium oxide because that's about 1.7 log units more oxidized than nickel oxide. And so that's in the reasonable range for arc magmas. And enough experiments have been done at nickel oxide that we know that basalts that are differentiating at about nickel oxide tend to track along Miyashiro's calc-alkaline tholeiitic boundary. So a question was, if we start out with something that's not super wet but it's plausible and is appropriately oxidized, what do we get? Well, this is a busy slide. It shows experimental results, but you can summarize the phase appearance rather simply. At high pressures, the early crystallization is dominated by olivine and clinopyroxene. Then that's followed by a gabbro interval or gabbro-norite interval, and then amphibole comes in. That's this line here. As I said, because there's CO2 in our samples, they saturate with the vapor phase. That's the vapor saturation. And then that early olivine-clinopyroxene interval gets narrower as one moves to lower pressure and is replaced by a broader range of gabbro crystallization. These are the fundamental results. Result melts at 9, 7, and 4 kilobars. You can see they produce medium K andesitic liquids. At 9 kilobars, the liquids climb up slightly into the tholeiitic field, and then they track along the tholeiitic calc-alkaline boundary. But at 7 and 4 kilobars, they drop rather neatly into the calc-alkaline andesite field. So at not unusually high water concentrations and not unusually oxidized conditions, arc basalt produces calc-alkaline andesite. It doesn't need to be very complicated. A question, though, and then we don't answer this question, is how oxidized are primary arc magmas? There is debate on that question. It may be that they're not as oxidized as rhenium oxide, in which case one would have to come up with a more complicated model. I think I'll skip this. Well, the main point is that the alumina enrichment varies with pressure. That's an indication of plagioclase. Many arcs erupt high aluminum basalts that are nevertheless pretty fractionated, and many of us hypothesize that the process that creates those evolved high aluminum basalts is crystallization in the deep crust of a pyroxene-dominated assemblage, and that's what this is showing. You're getting sort of 19 to 20% alumina in liquids that are near the basaltic andesite transition. But one thing that is different about our results versus nature, so these contours, this is the alumina saturation index. That should be 2 times calcium there. So things that are above 1 in this diagram are paraluminous, and things that are below 1 are metaluminous. We find, and other groups find as well, that crystallization of basalt at deep crustal conditions tends to produce liquids that climb into the paraluminous field while they're still andesites. And this is one of the motivations that we had for actually doing this study. I had seen results that were coming out of the Zurich lab, and I thought, well, they must be doing something wrong. And so we tried everything that we could in terms of mitigating against sodium loss, about iron presaturating the capsules, blah, blah, blah. We got the same result that they did, production of paraluminous andesitic liquids. Now, at lower pressures, this is less of a problem. So 9, 7, and 4 kilobars. And then here's some results at 2 kilobars that fall right along the natural trend. And it raises a question of what really is going on. Even though we can make calcalkaline andesite, in terms of its iron to magnesium ratio and its silica content, they tend to be calcium deficient at high pressures. Maybe much of this array actually results from primitive basalts coming into the crust and mixing with evolved granitic liquids that are in this region here, creating that array. Another possibility is that we're all suffering from some kind of a kinetic problem that we haven't resolved. So the conclusions, I think I've said them before. Production of high alumina, low magnesium basalts and basaltic andesites can result by deep crustal crystallization of abundant clinopyroxene. These then lead to production of andesitic melts and acidic melts. They're calcalkaline. Production of liquids with low iron to magnesium ratios, characteristic of andesites and dacite, are due to both magnetite and hornblende crystallization. But there is this problem of liquids becoming paraluminous while they're still andesites at deep crustal conditions. And that's an interesting problem to address. Thank you.
Questions? Shout 'em out
Just
if
speak
you've got
up, because we can't see anything up here. No? All right, thank you.
it. Tim.
This paraluminous thing is something that we discover over and over again. You don't see it in erupted products of volcanoes very often, but you can see some evidence for the sort of residues of paraluminous melts crystallizing in the lower crust of the upper mantle.
Yeah, I think it's a real thing. We did it. The Zurich lab has done it. Your lab at MIT has done it. So unless we're all suffering from kinetic problems, which I don't think so.
Well, we may be suffering from other problems.
We may be. Yeah.
The favorite rock type that's characteristic of this is Perugia.
All right. We got a question. It looks like Peter Michael, you have a question?
The difference between the experiments and the natural liquids have anything to do at all with the fact that it takes quite a while for plagioclase to kick in. If the zone plagioclase into your natural liquids, your experimental liquids.
Well, what happens, I mean, I won't force you to go back to that. You saw that the liquids go up in ASI, and then they bend over, and then they tend to track parallel to the natural magma array. That bend over where they track parallel to the natural magma array, if I can, takes place once they've saturated with plagioclase. So they climb and climb and climb in ASI without increasing a lot in silica, and then they saturate with plagioclase, and they stop climbing in ASI anymore. So if there's a nucleation problem with plagioclase, then that would be an explanation. Another possibility is that, and this would also be controversial, is that common parental arc basalts are a lot drier than we think they are. So they saturate with plagioclase much earlier. So there's things to work on this that will be interesting to develop. Thank you.
We're actually a little ahead of schedule, so I'm going to wait for just a minute or two to make sure that everybody who wanted to see Ollie is going to be here. If there's any other discussion, of course, we can continue that so Tom doesn't get off the hook too soon, or of Elizabeth's excellent talk before, if she's still here.
Yeah, I have a few extra slides.
Okay, well, we'll just press on then.
You don't see anything here.
Yeah, you don't. Get ready. So this is going to go the yellow at 11 and red at 13.
Is it?
Okay.
Okay.
So our next speaker is Ollie Jagouts and Max Schmidt. The title of the talk is The Arc Delaminate, a Geochemical Reservoir Twice the Size of the Continental Crust. It's one of our invited talks.
Okay, first of all, thanks for the invitation, and then I want to add also that I added a last-minute co-author on this talk because I included a few slides of work I did with Mark Bain recently. And so when we talk about how continental crust is formed in arcs, we all somehow agree that we start from a primary basaltic magma or a primarily andesitic magma that is in equilibrium with the mantle assemblage, which in this silica against magnesium diagram is at a lower silica and higher magnesium concentration than the bulk continental crust. And so you can envision your favorite path, how you go from this black dot to the red dot here and explain the bulk composition. You can either go directly or you make a more complicated method by mixing different parameters. But it doesn't matter. Even in the case of an high magnesium andesite, you somehow have to lose a component that is very low in silica and high in magnesium number in order to make the bulk composition move from the black dot here to the red dot. And so that has been, of course, proposed many years ago that we have to lose this composition. And currently we discuss two main mechanisms. There is the new idea of Hacker and co-workers that we somehow have a density sorting mechanism of material that goes down along the oceanic lithosphere, where we lose the dense stuff that goes down and we add buoyant stuff back into the crust. And there's the old idea from Goldstein and Arndt and Kay and Case that we have buoyant stuff preserved in the arc, which ultimately then might produce the continental crust, and we lose stuff at the dense stuff at the mantle crust interface in an arc. And so what we try to do is try to get some idea from the area we work in Kohistan, what the magnitude of this flux could be in order to produce an andesitic arc crust. Is this not fine, the color?
It's a better pointer.
You like the color better? All right.
It's just bright.
Okay, so the other problem we try to address at the same time sort of is that when you want to produce continental crust, and this is just a seismic velocity structure of an example from the continental crust from southern Spain here. So the continental crust is characterized, as we all know, by this significant jump in the seismic velocity around 40 kilometers, where we increase the VP velocity about 1 kilometer per second. And we all know that we call this the moho, which we think separates some sort of upper mantle peridotite from the lower crustal gabbroic rocks. And so when we look at the seismic structures of arcs, even so in arcs like the isobonin, where we have the intermediate composition preserved, the lower crustal seems to be very different in terms of its seismic properties. So if we want to produce continental crust out of this material somehow, or if Earth produces continental crust out of this material somehow, we have to explain as well the composition as well as the difference in the seismic characteristic. And so I just read out the seismic characteristic of the isobonin around 250 kilometer arc length here, and that is this blue line here. And you see that on average, the lower crust in arcs seems to be faster than the lower crust in continents at the same depth, and then they seem to be a bit slower in the mantle. And that becomes more apparent in this slide here, where we just looked at the distribution of seismic velocities in continents, here shown in red, which is the Christian and Mooney compilations, and then in arcs of rocks that lie above the moho, which people identified. You see that the seismic velocity is relatively similar for continental and arc rocks, but when you look at the rocks that are classified as lying below the moho, you see that in continents it seems like the rocks on average about a half a kilometer faster than the rocks that are assigned submoho in arcs. So somehow we have to change that if we want to produce continents into arc crust into continental crust. And so to understand this delamination mechanism and the magnitude of it, it is important if we want to understand the mass balance in subduction zones. We can approximate how fast arc crust growth, and there's a lot of discussion about it, but in principle we can achieve numbers here. We can also approximate what subduction erosion and sediment subduction to a certain depth in the mantle might do, and we can approximate relatively easy what the crust production rate is in divergent plate boundaries. But it's relatively difficult to know what the arc magma flow is because we don't know what kind of a composition and how much of compositions delaminate at the base. And in principle, if we would know the arc magma flow and we know the average degree of melting, we could also say something about the magnitude of the corner flow of new mantle material we bring in the melting region. And so what we try to do is approximate what this number here is. And the problem why that is not a simple thing to approximate is because only if the composition of an arc is equal to that of a parental arc melt, the arc production rate is equal to the arc magma flux. And I guess we all agree that arcs don't have a primitive melt composition. So in that case, even if we ignore sedimentation and erosion, the arc production rate is whatever comes out of the mantle minus what we stuff back into the mantle due to delamination. So if we really want to approximate this, we need to know the composition of an arc. We need to know the composition of parental arc melts, which is relatively one of the easier parameters to constrain. We need to know the composition of the material that is delaminating, and we have to do the mass balance between all of them. And so we try to do this naturally in the Kohistan arc, and the reason we can do it there is because in the Kohistan arc, from the southern exposure here to the most northern exposure in the north, we have a complete arc section exposed from unmetamorphosed volcanics here in the north to ultramafic cumulates in the south. And so what we did in the last few years, we mapped as much as we can of this arc, and we can establish a stratigraphy where we go from volcanic rocks through the plutonic rocks, through more of the gabbroic rocks in the base, and then garnet granulites, hornblendite garnetites, and ultramafic cumulates at the base. And we could establish a stratigraphy of the arc, and we could do PT constraints, pressure constraints, and we could prove that the entire arc section is actually exposed. And so then we went and we integrated the composition of the arc using nearly 600 whole rock compositions and approximated thickness of different mapped plutonic units. And we did this by approximating the thickness here as well by mapping their contacts in the field and using barometrical estimates for their thickness. And based on that, we approximated the composition of the arc, and the results are shown here for these two estimates. So in blue, that is the mapped thickness. In red is the barometrically constrained thickness, compared to the Rutnik and Gao estimate for the bulk continental crust. And so to make this story short here, the important thing is that the bulk composition of Kohistan is andesitic and essentially very similar to the bulk continental crust. There are some discrepancies here for the high field strength element and for the more incompatible trace elements, but for the sake of this talk, I don't think it is so significantly different that we shouldn't call it continental crust. So we think that the composition of the Kohistan arc is essentially that of juvenile continental crust that could be formed in arcs. And so in the second step, we approximated the bulk composition, the composition of primitive arc melts. We did this by compiling lava composition and primitive volcanic composition from the GeoRock database. And we used this criteria of high XMG, high nickel content, and high chrome content. And we searched through the database, and we found different volcanic rocks which have these characteristics. And then generally in this talk here, I focus on basaltic composition, even so these high magnesium andesites do exist as well. And we have this composition as well for the Khoistan, where we have primitive arc lavas, which we use to approximate this composition. So we have different parental melts. We have the arc composition. So the last thing we need to know is the composition of rocks that could delaminate. And the way we did this, we used our stratigraphy of the arc, and we used Perplex to calculate the subsolidous phase assemblages of all these different rock compositions. And here are two examples shown. If I go back, this is a garnet granulite here and the garnet hornblendite. And this is the example of the garnet granulite and the garnet hornblendite here. And what you see here in this diagram of pressure against temperature is the density difference of the rock we are interested in against the subsolidous phase assemblage of a depleted upper mantle. And so everywhere where this diagram is color-coded, the rocks we are looking at are more dense than the underlying mantle, and thereby, of course, in detail, depending on viscosity, you could delaminate and bring them down into the mantle. So if we do this, it turns out that roughly the uppermost 40 kilometers or 37 kilometers of the arc are density stable, whereas these rocks here down there are density unstable. And we have around 10 kilometers of these rocks preserved. So we have a significant outcrop here where we have density unstable rocks preserved in Khoistan. And so we can go in the field, sample them, and measure their composition, and thereby we have some idea of the composition of the rocks that delaminate. And when we did all that, we actually had all the ingredients to do a mass balance. So what we did is we calculated a simple mass balance where we used the ultramafic composition, the bulk composition of the continental crust, or the Khoistan arc in this case, and match it to the primitive melts of basaltic composition. And the key of this plot here is that if you have a certain volume of melt, you have a bucket of melt, you have to lose about 60 to 70% of that melt composition in order to produce an andesitic crust. And so that's the key point of this talk. If we produce continental crust from basaltic arc magmas, we have to lose about 2/3 of the volumes of crust we see by delaminated material. Okay, and that's also in accordance with experimental investigations. And so because we know now the composition that is foundering, we know its magnitude in respect to the crust preserved, we can integrate all these numbers here, and we can show that the arc magma flow is about 2/3 of the magnitude of the basaltic volcanism along divergent plate boundaries. So it's a very significant, and as you all know, this number here can change significantly. But equally, we also see that the amount of material that is delaminating is about 1/3 of the subduction of the oceanic crust. So it's a very significant second return flow that we have at the base of an arc into the mantle in order to produce an andesitic arc crust. And so the question is when and where that exactly happened. So recently I started working with Mark, and what we did is we compare the outcrops of the Khoistan arc here on the left with the Talkeetna arc on the right. And so it's a very busy slide, so I walk you through in detail. But here on the left side, we have our stratigraphic column of the Khoistan arc. Here on the right side, this is Peter's stratigraphic column of the Talkeetna arc. And they're actually very similar. So here in Khoistan on top, we have the volcanic rocks. Then we have the felsic plutonic rocks that make up the Khoistan batholith. And then in the base, we have the gabbroic rocks here shown in blue. The purple rock is the garnet granulite. These are the hornblendite garnetites, and these are the donites and pyroxenite ultramafic cumulates. And so these colors, they're supposedly matching those colors here, where we calculated the average VP velocity of these different units shown here as blue dots for the Khoistan, and the density, and in red dots here for the Talkeetna. I walk you quickly through the Talkeetna section as well. So in Talkeetna, they find the volcanics on top as well. Then they have the felsic plutonic rocks. Unfortunately, then they have a significant gap in the preservation record. It's not quite clear what is actually preserved. There's nothing preserved here, sorry. And then the base, we find gabbroic rocks, and then we find a very thin layer in the Bernard Mountains of garnet granulites and pyroxenites, and the way I've drawn it here is exaggerating their thickness. They're only a few tens of meters thick. And then Talkeetna is underlain by an upper mantle rock of Harzburgitic composition. Okay, and so we calculated as well for the Talkeetna and the Khoistan the seismic velocity and the density of the average composition of these rocks, and we compare it to the isobonin seismic velocity here shown in blue and the seismic characteristic of the continental crust of Christian and Mooney. And let's discuss the density first. So what you see is here is the density of an upper mantle at these conditions here. And what you see is that the density, the Khoisan arc is density unstable from about 40 kilometers depth onwards. And so we have a potential to lose these rocks here and sink them back into the mantle. And that fits very nicely to what we see in the Talkeetna arc, where we have the transition from crust to upper mantle, and we see what we think is only relative amounts of these garnet granulites. And so you can see that in the Talkeetna, the section is essentially successfully density sorted. And when we look at the seismic velocity, you see that the Khoisan doesn't really display any significant jump in seismic velocity. We don't really find a moho here. Whereas in Talkeetna, this transition between the gabbroic rocks and the underlying mantle is associated with a more significant jump in seismic velocity. So it's possible that the difference between our crust and continental crust is that you lose this density unstable material exactly there where we find the moho in continents, and you replace it by unrelated upper mantle material, and thereby the location of the moho is the former garnet in isobar. But now, when it's density sorted, it is, of course, a crust-mantle transition. And so the question is when this happens. And so we used the calculations of Joule and Kellerman and added it to our magma flux rates. And what you see here is a calculation where we look at the moho temperatures against the thickness of accumulate layer that would be stable based on density and viscosity considerations. So that everything that is plotted on the right side of these lines here is density unstable and would delaminate, whereas everything that is on the left side here would be preserved. And what is shown is this different arc magma flux and different density differences. And these boxes give the time it would take to build an unstable layer in million years. And what you see, and what we all know already from Joule and Kellerman's calculation, that around 800 degrees there is an increasing thickness, layer thickness becoming stable. That's because of the temperature-dependent viscosity. And so the interesting thing is when we compare the moho temperature between Talkeetna and Khoisan, Talkeetna we estimate temperatures of around 1,000 degrees at the moho, whereas in Khoisan we think we were significantly colder, less than 800 degrees. And because of that, it looks like that in Talkeetna you would delaminate a layer that is about a few kilometers thick every million years or so, whereas in Khoisan you would build up a layer of around 10 kilometers thickness, and it would take you somewhere between 15 and 5 million years to delaminate it. And that fits very well with our observation of the layer of density unstable material preserved in Khoisan. And that leads me nearly to my last slide. And so when you look at the seismic velocities of the rocks that are preserved in Talkeetna and in Khoisan, you see that they match very well the composition of rocks that are associated to be lying above the moho in continents and in arcs, whereas those rocks that are density unstable in Talkeetna and in Khoisan have seismic velocities typical for those rocks people consider lying below the moho. And then, of course, the Talkeetna mantle, if you calculate the seismic velocity, matches very well with the seismic velocities we see underneath continents. And that then leads me to my conclusion. So I think we see that there is a significant hidden mass flux at the crust-mantle interface, which is about twice the size of the preserved andesitic arc crust, and that this foundering of this density unstable material could explain the location and the characteristic of the continental moho. Thanks.
One quick question while we do the changeover. Shout it out because I can't see anybody up here.
Well, so I mean, some of the material that delaminates there has alcohol in that. So there's a certain limit in stability, and currently Max actually doing an experiment what happens to that. Tatsumi has shown yesterday experiments stated that some of this material, which they calculated based on their model assumption, might sink through the 660. So, I mean, I think we should look at it, what the fate of this material is. The real answer is no.
Thanks. The next talk is entitled Rethinking Recycling in Arcs by Kellerman, Bain, and Jagouts. The speaker is Peter Kellerman.
So I figured that Ollie would probably cover all that. If you read our abstract, we have, 10 different talks there. But so I thought I'd focus on just one thing. And first of all, congratulations, Max, very deserving, and then we see, in these talks here, all your contributions to this field. Just to, restate the problem, primitive arc lavas. I made this figure a long time ago, and I thought it meant something it doesn't mean. But primitive arc lavas are mainly basaltic, okay? Whereas continental crust is somewhere in the andesite to dacite range. And this is often referred to as the andesite paradox because for lots of geochemical reasons we think continental crust forms mainly in arcs. So this is another diagram that I use a lot just to get your eye used to it. The pink estimates are a compilation of bulk continental crust estimates with Rudnick and Gau's very authoritative papers here and the Hacker et al. Estimate from EPSL last year. Over here, kind of bracketing the data. Well, I'd say we don't really know where the bulk composition of the continental crust is, but we'll just draw a polygon around all of these and call it good. And again, arc lavas do tend to reproduce these geochemical characteristics and many others, which is why a lot of people think that arc magmatism is important in continental genesis. And just to remind you, mid-ocean ridge lavas just don't go there at all. Here's that polygon for continental crust. Here's a whole bunch of glasses from these Pacific rise and the mid-Atlantic ridge, and it just doesn't happen. And just to get you used to this, this is now continental crust normalized spidergram, or trace element, extended trace element diagram with a bunch of mid-ocean ridge compositions. This is the range of continental estimates from that compilation. Fortunately, on 3 orders of magnitude, it looks kind of narrow. And you can see that these mid-ocean ridge basalts are very, very different. Okay, so first going to the elutions and reminding you that there's some parochialism in the elutions. What we call the central elution or oceanic elution arc over on the right here is a little bit geochemically different from what we call the western elutions on the left. If we look at the elutions east of Adak, the average lavas are actually basaltic andesites with an Mg number of about 45. And obviously, if the bulk composition of the arc crust is coming out of the mantle, it's sitting somewhere up here in that part of the world and very, very different from continental crust. But the average lavas are actually pretty close. If we look at the average lavas west of Adak, they sit nicely within this field for continental crust. We don't probably know exactly what the primitive magmas are in the western elutions, but regardless, if the bulk composition of the incoming primitive magma sits up here, it's different from continental crust, but the average lavas are very similar to continental crust. And finally, the elutions are kind of nice and unusual in the world of intraoceanic arcs in having lots of exposed intermediate to felsic plutons on the islands. And here's a data compilation for those plutons, and the average composition sits squarely within the bulk composition of continental crust, although again, primitive magmas must sit up here, and the initial bulk composition, if you like, might sit up there. If we look at the trace elements, this agreement continues to be remarkably good. So remember the mid-ocean ridge basalts falling off at the incompatible end of this extended trace element diagram, looking nothing like the compiled continental crustal values in gray. In the elutions, if we sort for felsic plutons, we get this filled blue symbols. If we sort for relatively intermediate to felsic lavas, we get these red symbols. If we add them together 50-50, we really can get a composition that sits right inside the envelope of estimated continental crust for essentially any element you might care to name. So the problem with, for me, the problem with this delamination idea that you've heard about earlier and you'll probably hear more about today is that it's really kind of inefficient. You can only throw away the material that's below the garnet in isograd, and that is typically going to be 2/3 of the way down or more in magmatic arc crust. And so we can imagine geological scenarios where this kind of material goes through the washing machine a gazillion times and all of it basically finds itself in granulate facies sooner or later and decides that it would like to go down or up. But what has excited me in recent years is to think more about what happens when, for example, arc crust or trench sediments or sediments of any kind subduct on top of a mafic plate. And so In the elutions, for example, you have a relatively, as I showed you, average lava compositions are intermediate, average pluton compositions are intermediate. Those are sitting in the middle to upper crust. If that material subducts, we get to have all this material go through basically eclogite phases and decide if it would like to go up or down. And it seems to me that this is potentially a much more efficient density filter. Okay, so we can come up with all sorts of fancy ways to think about that, so we can maybe have imbrication of material directly from the forearc into the arc lower crust. You can have things going down and magically coming back up the subduction channel, which is probably Brad Hacker's favorite, or we can have little blobs of stuff floating up through the mantle wedge. But what was pretty clear is that buoyant material at the top of a subducting plate does not go into the lower mantle. And so we can use this. So I'm going to concentrate here on just a couple of things. Here's a seismic section for a long strike section for the elutions from Donna Shillington's work. And what you see is that the lower crust has lots of velocities greater than 7.2 kilometers per second. Nobody thinks that these are not mafic rocks. But on the other hand, the mid-crust is probably composed largely of intermediate plutons, and I showed you already what the upper crust is made of. So if this arc gets subducted, or if chunks of that arc get involved in subduction erosion, or if trench sediments are derived from this andesitic material on the top of the crust and are subducted, all those things can go through density sorting, and we can have the felsic parts returned to the surface or near the surface. So here is a diagram. You can't see it very well. I guess I made this a little too gray. But in the background here are now calculations of there's compositions, black and red, for this whole compilation of elution lavas. The black ones are denser than 3375 kilograms per cubic meter at 3 GPa and 700 degrees C. And, sorry, the black symbols are denser, and the red symbols are less dense than 3375 kilograms per cubic meter at 3 GPa and 700 degrees C. So these red rocks would be buoyant with respect to the overlying mantle, and these black rocks would be neutrally or negatively buoyant with respect to the overlying mantle. And the average of the red stuff sits at that big star. If we then look at that density sorting and we do the same thing for the plutons, we see again, if we add about half plutons and half buoyant lavas, we get this trace element pattern that corresponds very, very well to continental crust for basically the periodic table. The Marianas, I used to think, was a very poor place to go to look and think about these kind of processes, because you can see, without doing a lot of work, that the average lava is not going to sit anywhere near continental crust, and probably everything entering the crust is a primitive basalt, which I used to look down upon. And similarly, the trace elements in Isobonian Marianas normalized to continental crust show this very strong depletion in highly incompatible elements for, again, lavas that are sorted to kind of look like continental crust. And this was a mistake, I would say, in retrospect. But I used to use this slide to say, this is a terrible place to go and think about the genesis of continental crust. Okay, so we do the same thing for this great compilation from Erica Jordan of IBM lava compositions. Black ones are denser than, or as dense as, the overlying mantle at 700 degrees and 3 GPa. Red ones are buoyant. The average buoyant composition is, you know, we would let this into the club of upper continental crust. We would give it a fellowship in the upper continental crust union. And then, I haven't got a nice slide yet, but there are these plutons, as many of you know, where the Isobonian Mariana arc kind of collides with southwest Japan. There's the Kofu granitic complex and the Tanzawa tonalites. There's actually a seamount out here that has felsic plutonic rocks as well. So we can compile those data and get some notion of what the mid-crust in the Isobonian Marianas arc might look like, and that average composition sits right there. And then when we do this trace element thing, it just doesn't turn out anywhere near as badly as I used to think. So that average composition here is now grayed out, and it is indeed very depleted in highly incompatible trace elements with respect to continental crust. But if you do this density sorting process, you end up with, what the heck happened here? These are lavas in red that are more buoyant than the overlying mantle, and these are plutons that are more buoyant than the overlying mantle, and you add them together, and it's not perfect, but it's really remarkably good. And it's an awful lot like the Aleutians once you decide that you're willing to throw away 90% of the lavas. Okay, so just to summarize, here's Aleutian lava compositions, averages. Here's Aleutian plutons. This is the average of the buoyant compositions from the lavas and the plutons at 700 degrees and 3 GPa. These are the IBM averages, buoyant compositions, and these are the trace element diagrams that correspond to those values. Just one more thing, the Western Aleutians is the isotopically depleted end member for arcs worldwide. And so when we see material there that looks more or less identical geochemically to continental crust, that is juvenile continental crust. This is not recycled components from continentally derived sediments. This is brand new stuff. So whatever the process is that creates that material, it is happening in the Western Aleutians today, and it's a particularly good place to study it. Thanks very much.
Questions? Again, shout them out because we can't see.
Dan.
This stuff goes down. Usually it comes back up again something. Would it have any special signature when it gets normalizing, which is with respect to mean continental crust, makes it a little hard to see whether there's any special property. Would we recognize it melted? Would we recognize it as nodules?
Well, I mean, it's isotopic. It's in the Aleutians anyway, that material is isotopically very primitive. So it's quite distinct from continental crust, average continental crust in that way, usually. But I want to turn it around a little bit and ask the question, if these things rise into the arc crust. I know, but I'm going to, a bigger, you want a bigger loop. Oh, I see. I don't think it can go that far, Dan. We may not understand the rheology of the upper mantle very well, but if you just sort of plug and chug with the flow laws available to us today, once you have a density contrast of 50 or 100 kilograms per cubic meter at a layer thickness of more than 50 or 100 meters, and the temperature is up over 800 degrees C, these materials are going to separate. You can't really get granodiorite to go down and show up on a mid-ocean ridge.
Depends on texture.
Yeah, I mean, if you make it really thin.
I'm simply asking from a geochemical point of view, rather than a thermodynamic. What would one do?
Well, these are very highly, I never thought about this, but these are very highly incompatible elements. So a lot of the ratios will look like continental crust, but isotopically it's going to look primitive to you.
No, this is the stuff you're talking about.
Oh. The dense stuff. Oh, I'm terribly sorry. We've been talking past each other the whole time. The dense stuff.
Peter, talking to the microphone.
Really?
Yeah.
Okay.
It's for the
Hi,
record,
back there.
not for the
Oh, I see. The dense stuff. Well, again, the fractionation process is not terribly important, but I would look for a garnet signature in as much as if there's any melting associated with this process at all, then the dense residue ought to be heavy rare earth element enriched.
I would thought very strongly.
Well, that depends. I mean, you realize nothing I said here involved melting at all. There is a bunch of possibilities, and we've written about them before, and we will again along those different trajectories. But right now, I'm just talking about mechanical movement of things.
Thanks, Peter. The next talk is entitled Effects of Light Elements on Silicon, Oxygen, and Sulfur on Siderophile Element Partitioning between Liquid Iron Alloy and Silicate Liquid at High Pressure. The authors are Ruby, Nakajima, Rose Weston, and Froston. The speaker's Dave Ruby. Here's your pointer. This will go yellow at 11 minutes and
So
red
to
at 13.
advance,
You want to use this one here because you're on the PC.
okay, right.
And you're good to go.
Okay, well, first of all, I'd like to thank the organizers very much for inviting me. It's a great honor to be here on this occasion in this symposium in honor of Max receiving the Dana Medal. So my talk is going to be on a totally different theme. I'm sorry, I'm not going to be talking about arc magmas, but I'm going to be talking about high pressure. And about a long time ago, maybe 18 or 20 years, Max spent a year or more in Bayreuth supervising the multi-anvil lab. And at that time, I had the impression that he was not a very innovative experimentalist. Well, when he got to Zurich a few years later, it turned out I could not have been more wrong, because in Zurich he has done some incredible things, establishing some wonderful, innovative facilities like multi-anvils, which turn upside down so that you can mix the contents of the capsule. He's put a piston cylinder on a centrifuge, and I think recently there was even a plan to put a laser-heated diamond cell on a centrifuge. So it's very appropriate here to be talking about results obtained at high pressure. Okay, well, I'm going to be talking about siderophile elements, and of course the main constraint that we have on core formation in the Earth comes from the concentrations of siderophile elements in the Earth's mantle. This is because during core formation, the siderophile elements partition into liquid metal, which goes into the core, and these elements are therefore depleted in the mantle. And the degree of depletion depends on the pressure, temperature conditions, oxygen fugacity conditions of metal silicate segregation. So the way of constraining core formation is to perform partitioning experiments of siderophile elements between liquid metal and liquid silicate under various conditions, and then put the results into models of core formation. Okay, so now there's a potential problem here, because the Earth's core has a density deficit of around 10% compared with pure iron-nickel alloy. And this density deficit is certainly caused by light elements in the core that potentially include silicon, oxygen, and sulfur. Other elements have also been suggested, but I'm going to be concentrating on these today. So recent core formation models from our group and from Bernie Wood's group suggest that there could be around 8 weight% silicon in the core, 3 or 4 weight% oxygen, and Bill McDonald was favorite concentration for sulfur is about 2 weight%. So the question is, do the high concentrations of these elements in the liquid iron alloy affect the partitioning of siderophile elements between metal and silicates? So this might be a crucial question for understanding core formation. Okay, so this is the thermodynamic bit. The activities of iron and the element of interest, for example, nickel in a liquid iron alloy, can be expressed in terms of the Wagner formulism modified by Ma in 2001. And we have here an expression for the activity coefficient of iron in the liquid iron alloy, and an activity coefficient for element M. I'll be mostly talking about nickel in the liquid iron alloy. And we have a lot of compositional terms here, the silicon content, the concentration of nickel. And what's important here is that there are 3 critical interaction parameters. There's a silicon-silicon interaction parameter, a nickel-silicon interaction parameter, and a nickel-nickel interaction parameter. So if we can identify these interaction parameters, we can get the activity coefficients and then describe the thermodynamics of the liquid iron alloy. Okay, so the interaction parameters are formulated to be a function of temperature, inverse temperature. So as temperature increases, the interaction parameters become smaller and the system becomes more and more ideal. And at infinite temperature, these will be 1, and the system will be completely ideal. So this is the temperature dependence that's considered to be applicable. Nothing is known about the effect of pressure. Okay, well, Bernie Wood has been working on these systems for quite a few years. So here are some results from a publication from his group in 2011, and this shows the effect of silicon dissolved in the iron alloy on the partition coefficient of nickel. So we have weight percent silicon here up to 25 weight percent. Here's the metal silicate partition coefficient for nickel, normalized to the partition coefficient for iron, which removes the oxygen fugacity dependence. And we can see that there's a very large effect. If we have 10 weight percent silicon in the metal, the partition coefficient is reduced by almost 1 order of magnitude. So this is at 1.5 GPa. And here are some results for 6 GPa, which also show a very dramatic effect. So these results were obtained at rather moderate temperatures in terms of what's likely for core formation. So the question is, if we extrapolate to much higher temperatures, do we get the right result? So we've been doing experiments at temperatures approaching 3,000 Kelvin in the multi-anvil. These are at 25 GPa. And so here's the log KD. This is the distribution coefficient that we saw in the previous slide versus the weight percent silicon in the metal. And now we have a much smaller effect. With 10 weight percent silicon in the metal, the partition coefficient is reduced by about 0.2 of a log unit. In the previous slide, the nickel-silicon epsilon interaction parameter was about 7, and now it's reduced to 3. And this is actually very consistent with the tough data. So the red line here shows a fit to our data, and then the green line here shows an extrapolation of the Tuff et al. Data, and within the errors, these are basically the same. So we can extrapolate at least to 3,000 degrees from the low temperatures safely. And similarly for cobalt, the cobalt-silicon interaction parameter here is about 3.5, and the extrapolated Tuff et al. Results are very similar to our results at 2,900 to 3,000 Kelvin. So this all looks very nice. Now this introduces a really big problem, because in order to formulate the exchange coefficient Kd, we need to know the valence of the element, like nickel, in the silicate liquid. And for nickel and cobalt, this isn't a problem. These certainly have a valence of 2, but for other elements, the valence is very uncertain. And the way of determining the valence, the traditional way, is to determine the log partition coefficient as a function of oxygen fugacity and plot it up, and then the slope of this line. From the slope of this line, we can determine N, the valence. So this has to be done over a fairly wide range of oxygen fugacities. And to get low oxygen fugacities, the traditional way is to add silicon to the sample. The silicon goes into the liquid iron and reduces the oxygen fugacity. But of course, if it's also causing interaction with the element of interest, then we're likely to get the wrong valence. And in 1999, our group published a paper by Gessman et al. Where we determined the valence of nickel using this method, and the answer came out to about 1.5 to 1.6. So this result was totally consistent with what we've seen in the last couple of slides. Now, as I say, for nickel and cobalt, this is not a problem, but for tungsten, it's a really big problem. So this is the expression for tungsten, Kd. Here's the valence, N, here and here. And we've done experiments again at 2,900 Kelvin as a function of silicon content. And now we can see that silicon has a really big effect on tungsten partitioning of a 1.5 or 2 orders of magnitude reduction. This is now in mole fraction here. So we fitted the data. We've got 2 fits here, one assuming a valence of 4+ for tungsten in the silicate melt, and one assuming 6+, and the fits are identical, but the interaction parameters are very, very different. 23 is the tungsten-silicon interaction parameter in this case, and 33 here. So we need some independent method of determining the valence of tungsten, and Bernie Wood has done this recently using XAFs and has decided that it's probably 6+. Okay, so I'd like now to look at the effect of sulfur on nickel partitioning. So we've done experiments mostly at 3 gigapascals and 2200 Kelvin. We've done a lot of experiments with different sulfur contents, so to look at the composition effect. And the first thing to note is that, well, we have sulfur contents in the metal up to almost 35 weight%, so this is FES on the right-hand side here. The first thing to note is that even though the pressure and the temperatures are not very high, we get significant amounts of oxygen dissolving into the metal, up to 3 weight%. So sulfur has a big effect on increasing the solubility of oxygen in the liquid metal. And Lee and Agee published some data a long time ago which also showed this. So high concentrations of sulfur in the metal result in significant oxygen concentrations, and so we could now have interactions involving sulfur, oxygen, and/or oxygen on the partitioning of siderophile elements. So this is now a plot again of log D for nickel versus oxygen fugacity, and we saw earlier that all the data should lie along a line defining a valence of 2+. For samples in which the metal contains no oxygen and little sulfur, these red symbols here, they lie close to this line, but all the other data here lie an order of magnitude or up to an order of magnitude below it. So clearly sulfur and/or oxygen are having a big effect on the partitioning of these elements. So if we plot up the log Kd for nickel against the sulfur content, we get some trend here. If we plot it against oxygen, we also get a trend, and there's no way of uniquely saying which interactions are important because we need 6 interaction parameters, and that's too many to obtain from such a data set. So what we've done is this is now the equilibrium constant, assuming that the activities of the components in the silicate liquid, their ratio is constant. So now we've got the activity of nickel in the metal and the activity of iron in the metal. And this shows the log of the equilibrium constant as a function of oxygen concentration. And this has to be independent of composition, and that's achieved with these 6 interaction parameters here. So 4 of these are taken from the steelmaking data source book, where there's many values from 1 bar data listed. This one here for oxygen is from a recent paper of ours by Suno et al. And the critical one here is the nickel-oxygen interaction parameter, which is 6, which is about 3 times larger than the value listed in the steelmaking data source book. So with these sets of 6 parameters, then we can describe this system pretty well. Okay, and then we have higher pressure data here, which should also be constant as a function of oxygen content. I think within the errors, these data here are constant, but we have very few data. And one thing here is that the change in going from 3 GPa to 10 GPa here is very large. The change going from 10 GPa to 15 GPa is a lot smaller, and this is consistent with a paper we published several years ago by Kegler et al. Showing a change in the pressure dependence of nickel partitioning with pressure. So one important thing here is that people often don't bother analyzing for oxygen, and if they don't do that, then they miss out on a critical interaction here. Okay, so I'm working on a project with Morbidelli and others at the moment to combine a multi-stage core formation model with N-body accretion simulations. So we can monitor the accretion of a planet from these simulations, and we assume that every impact between that body and a planetesimal or an embryo results in a stage of core formation. And we use a mass balance combined with element partitioning to determine the compositions of the silicate and the metal involved in such equilibration. So this is for an Earth-like planet here. This shows the percentage of the core that's formed, going up to 100%. And this is the concentration of the light elements in each batch of metal that results from an accretional collision. So we have several hundred collisions here, several hundred episodes of core formation, and the exact details here will be quite model dependent, but I think the trends are very robust. So the reddish bars show the silicon concentrations, and the blue bars show the oxygen concentrations. So when the planet is very small, we get significant silicon in the metal, and because the temperatures are then low, the interaction parameters will be likely to be important. So this is one area where the interactions I've been talking about will be important. And then towards the end of accretion, temperatures are getting very high, above 3,500 Kelvin, and under those circumstances, oxygen and silicon partition quite strongly into the metal. So in this model here, we have 35% oxygen in the metal and 25% silicon. And in addition, in this region here, we're likely to have sulfur being added. So there's a very high light element concentrations here. And although the interaction parameters will be small at such high temperatures, the concentrations will make the interactions still quite very important. So in conclusion, silicon, oxygen, and sulfur dissolved in liquid iron can significantly affect siderophile element partitioning, and two scenarios where the effect will be significant is in during the differentiation of small planetary bodies when temperatures are low and interaction parameters are large, and in the late stages of Earth accretion when we have high temperatures and high concentrations. So, thank you.
Thanks, Dave. We have time for a question while we do the change over here, so shout it out, and Dave will answer.
Oh, yep.
Is the silicate or equal exchange equilibrium with the core?
Is the silicate Earth in equilibrium with the core? No.
Which way should it go?
Well, I think there's no thermodynamic equilibrium between the bulk of the mantle and the bulk of the core. I mean, Dave Stevenson pointed this out 20 years ago.
At the core mantle.
Oh, at the core mantle boundary, there'll be. It's almost certainly different at the base of the mantle, yeah, because of exchange with on a limited scale. I think it's a very complicated problem, what's happening at the core mantle boundary. And also it needs enormous extrapolations of data, of course, from low pressures up to 135 GPa. Okay.
The shallow people. For example, the Hawaiian pickle rich.
All right, yeah.
Thanks, Dave. The last talk in this session is entitled Deep Recycling of Carbon. It's an invited talk. It's only fitting that we invited Max to give a talk since there's no separate talk associated with the Dana Medal. This is the de facto talk. So the speaker is Max Schmidt.
Thanks, Greg. Where is it?
Yeah, here's you get your own.
Okay. Today I will talk about deep recycling of carbon, and I thank to all the speakers before about the kind words about me. This is stuff that we have done over the last 5-6 years in my group, and there's a number of people that contributed in various ways. Carbon reservoirs and fluxes, you all have seen such a figure in one or the other form. The biggest uncertainty in the reservoir is in the mantle, where there's like 1 order of magnitude uncertainty. This stuff is well known. And then you have three fluxes, three different types of basalts coming out. And if you look here, this is from Sleep and Sarnlid, and from Dasgupta and Hirschman, and from Marty and Telstikin. There's a spelling there. You see these errors are very, very large. Yeah, and if you sum them up and you try to make a mass balance, you have no idea if carbon is coming out or going down into the mantle. And I'm not going to give a talk about these budgets. I'm going to look at this one flux, which is the arc flux. And I'm going to make the argument that the arc flux is about 20% or less than the subduction flux. And how can I make such an argument? I do it based on phase petrology, on phase equilibria, in contrast to measuring the volcanoes. Yeah, measuring CO2 outputs in volcanoes is very, very difficult. You can measure one volcano, and the next one will be different, and the next one will be different. Maybe you can do an entire arc segment, but the next arc segment will be different, and the next arc will again be different. I'm very pessimistic that you ever get to a precise number by measuring these things. Just to remember you, this fluxes are oxidized and the mantle is reduced. And if I get to the end of my talk in time, then you will hear something about reduced mantle. The oxidized world. This is from Jamie Connolly. Jamie Connolly did a model calculation with Perplex, so it doesn't include any melting. It includes only subsolidus. You have a basaltic crust, you have a gabbroic crust, and you have a serpentinized mantle. The serpentinized mantle, you have to look at it, it's 25 kilometers of serpentine. Nobody believes that there's that much serpentine. So what he does, he calculates the water content and the CO2 content. So he has only CO2 in the basaltic layer with ongoing depth, removing the fluid. And even with this completely outrageously amount of water, what you see, you can flush out a tiny amount of CO2. You go from something like 3.5 to 3.2% of CO2 in the crust. So metamorphic reactions do not remove CO2. And the reason for this is a very simple one. The higher you go in pressure, the lower the XCO2 is in the fluid. And typically you have like 5 to 10 mole% of CO2 in the fluid. So conclusion number one, subsolidus reactions mobilize less than 20% of the CO2. Okay, melting. This is a melting diagram for carbonated pelites. And you see these experiments were set up in a way that we try to do the fluid absent melting. So no excess fluid, water stored in fungite, and CO2 stored in carbonates. It turns out that's not possible. You cannot pick a composition with an appropriate water and CO2 content and get a fluid absent reaction. There is a small, minor amount of melt in the subsolidus, but it's really small, a few percent. And then you get to this major reaction, fungite plus coesite plus CPX, results in some melting garnet. Look at these temperatures. This is 900 to 1,000 degrees in the subarc region. This is what you need to melt this composition. There, that's the subsolidus, 940 degrees, calcite, CPX, garnet. Then you get above the solidus 1,000 degrees, and still you have the calcite. Yeah? There's very little granitic melt, or phonolytic melt actually. It's 10% of melt, and you have residual calcite. So even if you melt it, you don't get the CO2 out. Interestingly enough, if you go to higher temperatures, which is this band here, you have a carbonatite melt and a silicate melt coexisting, and that becomes important later. Now, if you compile all the work that is done, you get to this diagram. In red, you have the wet solidus that is done by Nichols and Wiley, 94 or so, and then to higher pressures by Io Group and Hermann. In purple, you get a fluid-saturated solidus that's from Tsuno and Dasgupta. In brown, the line I just showed you before. In green, when you have CO2 only. And if you put some PT pass on this is a set by Arke, and this is a set by Syracuse et al. You see you might get to the wet solidus, but you never get to these reactions. I mean, you can argue what is the right temperature there, and so on, but this is really outrageously high. I mean, nobody really claims that you have 1,000 degrees at 3 GPa at the slab surface interface. Of course, you can get there if you produce sediment diapirs. Yes, that's a different story. Okay, so if you produce some granites, which is highly unlikely, the granites only dissolve 2 to 3 weight% of CO2. Yeah? And even if you have 10 or 21% of melt and the calcite stable, you're not going to mobilize more than half a weight% of carbon of CO2. So the CO2 stays in the crust. Melting in carbonated pelites is unrealistic. Mobilization of CO2 would require 1,000 degrees or so. If you do the same thing with basalts, that's the wet solidus in green, the one from Dasgupta et al. This is from Yaxel et al. It's of course the same. Basalts melt at very much higher temperature, so if you have carbonates, you cannot melt them out. So in general, there's no way to melt out the carbonates. If you don't believe me, I'm going to give you now an example. I'm going to spend the next 10 minutes on an example. where we melt out the carbonates. And what happens then is really interesting. So I'm going to take these melts and put them into the mantle. Why I'm doing this? I'm not doing this for general interest. I'm doing this for explaining a very peculiar type of volcanism in Italy, the so-called chamafugites. The chamafugites, they have primitive characteristic, high chrome, high nickel, or some of them. They have high magnesium, but they have a potassium-sodium ratio of 8. Yeah? That's highly remarkable. So they're ultrapotassic, they're ultracalcic, and they're primitive. And these chamafugites, they are erupted in this region here, and this region is at the same time the region of the highest CO2 flux in the world. Okay, from Pecharillo, who wrote a very nice book about the Italian volcanism, it was already suggested that these chamafugites are a mixture of some carbonated sediment and metal melt. And I'm going to take this melt out of the sediments, and I'm going to produce the red melt here. How do you do this? I mean, you do sandwich experiments. In a graphite capsule, you place the melt here, that's AM07, with some mantle. I used 3 different types of mantles and just simply let them react. I use different water and CO2 contents, and the way this was set up, I work at the constant potassium-water ratio, because if you do fluid-absent melting, you always will have a potassium-water ratio as in phengite, as in white mica. And then I vary the CO2. Okay, and this is how this experiment looks. The nice ones, you get huge autopyroxenes. This is like almost a millimeter, CPX, olivine, and melt. The melt is not quenchable. The melt looks like that, and it's actually very painful to get that polished, because as soon as you use any water, the alkalis are gone. But if you do this carefully, you get the right alkali contents. Of course, most of the experiments look rather like that. You have a little bit of interstitial melt, and we used carbon sphere extraction techniques to measure this melt. Okay, here's the result. Blue is the water-rich one with an XCO2 of 0.3. Purple is the middle one, 0.46. And this is the high CO2 one. And you see, this is the potassium over sodium ratio you start out with. With water, you actually gain some sodium from the clinopyroxene in the ultramafics. Otherwise, you more or less conserve this ratio. So we can, in using these melts, we can explain the potassium-sodium ratio. Now, silica, I use as a differentiation index. I use calcium. This is silicate. This is magnesium. This is XMG. So you get this array here. Of course, higher CO2, you get lower SiO2. That's very well known. High CO2 makes alkaline melts. This is the San Venanzo. You see it fits very well here. It doesn't fit at all here, and middle and somewhat there. So the only thing that you have to do, actually, you have to fractionate olivine. Yeah, from these, magnesium over calcium, if you fractionate olivine, you go this way. This is San Venanzo. These are arrays from other volcanic areas. And you see you fit these very nicely. Yeah? Okay. How do these melts look? These melts have a water content that is directly proportional to potassium. That is the way I set up the experiment. But you get CO2 in the high X CO2, you get like 6 to 8 weight% of CO2 in this melt that is in equilibrium with the mantle. Otherwise, you get like 3-4%. Okay. So why is this interesting? The prevailing model on how to make these CO2-rich magmas is to assimilate carbonates in the crust. Yeah? So this is isotopes, oxygen against strontium. Up there is marine carbonate, down here is continental crust, and you can mix that up. Yeah? So percentage is very easy mixing calculation. Down there is the mantle, and you see actually here are these chamafugites I'm talking about, the data from Holm and Munzgard. And you see they are on a nice mixing line of a marl, which has about 1/3 carbonate, and the mantle. And the argument was made, these carbonates are in the Apennine crust and to be assimilated. This is almost certainly wrong. If you do a calculation, so what you need is something like 30% of the sediment component. If you do a calculation, it turns out we know the eruption temperature, yes? And now we assimilate the carbonate. If you assimilate 15% of carbonate, as you would need for Vesuvius, you would need a primary melt temperature of 1450 to 1400 degrees. Assimilating the carbonates is energy-wise very costly. Yeah? You need a lot of energy to do that. If you want to get to the Sanvanansu camphogites, you would have to have a primary melt at 1620 degrees. That's absurd. Yeah? That would not be alkaline rocks, that would be komatiites. And there's nothing like that in Italy. Okay. I think we skipped this. What is the idea? This is from Spackman and Rutile. It's just redrawn a bit nicer. This is how they imagine the slab below Italy. You're having this slab window in central Italy, and what is plotted here are all the volcanoes that are younger than 2.5 million years. And all the camphogites are in there. There's a lot of other volcanism, but it's rather normal calc-alkaline. Like the Tuscany and Alba, that's much older, it's normal calc-alkaline. All of these, with these camphogitic characteristics, very potassium-rich, very CO2-rich, sit above the slab window. And the idea how to explain this, carbonated pelites melt at the trailing edge. The trailing edge gets very high. The slab is breaking off because the convergence rate goes almost to nothing, so the slab heats up. When it breaks off, the asthenospheric mantle flows in here, the stuff melts. It hybridizes in the mantle. These are the conditions. These are water and CO2 contents. Something around 1300 degrees is the best fit that is reasonable to get. Then you need 10 to 20% of olivine fractionation to get to the magmas we observe. That's normal. If you decompress the magma, you're going to lose olivine. And then down here in the crust, you do an unmixing of carbonatites. The part I didn't show, they're also observed there. So that's a very simple model, and you link this kind of volcanism to this trailing slab edge. It's a one-time shot. Yeah, you only can melt this once. And the period over which these are active is very short. They are active for a couple of 100,000 years, and that's it. Then it stops. Okay, so potassium and carbon-rich camphogites in Italy, an example of carbonated sediment melts. Yeah? We never see that in any other arc. I mean, it doesn't mean that you have to get it, but this is what happens if you do this melting.
Thank you.
I'm not finished.
Oh.
I have half an hour, not 15 minutes, if you remember.
Do you? Oh,
Yeah?
good.
I can finish if you're tired.
I didn't realize it was a half an hour.
It's a half an hour talk. Yeah. So, less than 20% subduction flux. Okay. So what happens to the other 80%? So 20% come out, 80% go down. And the interesting thing is, you get granites here on the wet solidus. You get phonolites if you melt with carbonate. And if you go to higher pressures, you get to carbonatites. And the next one, if you look at this phase diagram, you see all these positive slopes here. This is when you produce a silicate melt. And at 5 GPa, you change from a silicate melt to a carbonatite melt. Yeah? And that has to do with the fact that you have an immiscibility gap here. This immiscibility gap intersects with the solidus. There's a bit of a complex phase diagram. And at the moment where the immiscibility gap between silicate and carbonate melt intersect the solidus, the melt jumps from the silicate side to the carbonate side. And then you get this carbonatites here. Oops, wrong direction. You have to turn your head to the left. I didn't know how to do this easier. This is work published from Daniele Grassi. What you see here, this is the silicate melt down here, so you have to change scale, 5 GPa, and then you get carbonatite melts. And you see this is a complex zigzag solidus. We did it over this entire temperature range. So what is changing? Above 5 GPa, you have aragonite and magnesite. You have sodium in the jadeite, and you have potassium in phengite, or in the dry case, which is the red line without water in K-spar. At 9 GPa, the phengite gets unstable, and you get K-hollandite. The K-hollandite, the higher you go with pressure, the more the K-hollandite becomes stable, and it begins to retain potassium. If you go above 16 GPa, something like that, the clinopyroxene structure breaks down, and sodium has no place to go anymore. There is sodium in the calcium carbonate, 25 mole%, There is sodium in garnet, there's some sodium in K hollandite, but there's no real phase that likes sodium. So if you do melting, all the sodium goes immediately into the melt. I keep pressing the wrong direction. And these are these carbonatites measured at the solidus. They are carbonatites, calcium, iron, magnesium carbonatites, but they're rich in alkalines. Yeah, you see up to 8 GPa, you get 25% of potassium oxide in there. Then it goes down again, and at above 16, 17 GPa, you get very rich in sodium. So you have a high potassium-sodium ratio to this range, and a very low potassium-sodium range at higher pressures. I'm pressing the wrong side, sorry. Okay, why is this interesting? If you look at typical PT paths, and you can pick whatever you want, you see the slope of the solidus here is negative. So if it gets negative in PT space, you have quite some chance to intersect with this PT path. So one chance to make these carbonatites is here, but that's beyond the arc. It's much deeper. Actually, these melts with a very high potassium over sodium, they're prone to form something like the kimberlite source region. Then you get more or less parallel, and there's almost no way you cross the solidus unless you do something like deflecting the slab at the 670, then you go to the geotherm, or you do a stagnant slab somewhere in the mantle. So it's when you relax the slab in temperature, then these pelites are going to melt. It's unavoidable. Yes? You cannot bring them to the temperature of the mantle without melting. This brings us to this slide. In this region, you have these ultrapotassic carbonatites. If they go in here into the mantle, they will react with the mantle. If you want to know what happens there, you should go to the talk of Anastasia Golubkova on Thursday. This is prone for kimberlite source region. Otherwise, you can do something down here. We have done trace elements, and we have looked what happens to the isotopes, and it turns out that these melts, which, as I said, are unavoidable, bulk mixing is not an option. You cannot bulk mix these sediments into the mantle. They have to melt. If you take these melts, actually they're ideal to form the EM flavor of the mantle. Yeah? At 8 GPa, they are going down there, 1322, and you see there's the depleted mantle. If you do a mixing, then you get exactly to this arrays here. Okay, so alkali-rich carbonatites form from melting of carbonated pelites. They are high potassic to 15 GPa, above 17 they're highly sodic. If anything melts beyond the arc, it's certainly these carbonated pelites first. There's no other lithology that has a lower melting temperature. If we go to the reduced mantle, first question, what is the carbonatite solidus in the mantle? Second question, is the carbonatite solidus really relevant? What is the carbon species? And why is that so important? It's a bit evident. A carbonatite is highly mobile. It has a low melting temperature. Diamond, which is the reduced stable form, is of course immobile. Yeah? So if you convert from an oxidized carbonate species to a reduced carbonate species, you're mostly immobilizing the carbon. This is from Frost and McCammon. This is typically what you have between cratones. So the oxygen fugacity goes down, and the work from Rohrbach et al., they show that around 250 kilometer depths, you get metal saturation in the mantle. You get the metal saturation because iron disproportionation. You put some iron 3 plus into majorite or iron 3 plus in the lower mantle in perovskite. That's work from Dan Frost about 2000 or 2001, I can't remember. So they have clearly shown that at higher pressures, because you have iron 3 plus stable in the silicate phases, you get a metal melt because you have a constant oxygen content. Okay, if you look at the solidus of a carbonated mantle, up here an experiment at 24 GPa, 1750 degrees, you see down here that is a carbonatite, that is quenched carbonate melt. These experiments, this one here is a subsolidus experiment, and the black stuff here is actually the carbonate, it's magnesite. And you see in an alkali-free system, we did this on purpose, alkali-free, the solidus is more or less the same as the adiabat in the mantle. And you can select your potential temperature as you want. If you select the higher one, it's inside this range. If you select the lower one, it's not. But we should consider that they're alkalis. This is by Gauche. And if you have alkalis, it's lower than the mantle adiabat. So normally, the carbonatides would stay molten. It's actually very interesting. We get this completely different slope than the one from Dasgupta and Hirschman, which is this one. And actually, we did these experiments, and they're really consistent with an experimental error from Dasgupta and Hirschman. What happens here is related to the clinopyroxene structure. When the clinopyroxene breaks down, the activities of calcium and sodium change completely, and this is why the slope of the solidus changes. Now, carbon speciation. We have done two types of experiments. One type of experiment, we saturated the system in magnesite and in elemental carbon, and we used a metal iron iridium alloy. That's a technique that was first used by Stanio and Frost in 2010. And from the composition of this alloy, we can calculate oxygen fugacity. Yeah? So this is exactly on the equilibrium. We have done another set of experiments with different solid state buffers, rhenium, nickel oxide, and an iron capsule. This is one of those, but there you only get one phase. You get one phase at a given oxygen fugacity. So you see the magnesite diamond equilibrium is this white band here. Nobody would claim that the mantle would be significantly above iron restite at larger depth. So at larger depths, of course, carbonates are not stable in the mantle. You would have diamond. And this leads to a story that we published last year. You have the subducting slab. If the subducting slab equilibrates thermally with the mantle, you will get carbonatides. These carbonatides, they move into the mantle. In the mantle, they're going to react with the metal that is present in the mantle. You get iron oxide and diamond. So you freeze the whole system. So you get these regions in which you have diamond and iron oxide, but no metal. Now, if you bring these regions into an upwelling, the iron 3 that is ultimately responsible to have the metal, the iron 3 is going to go back to iron 2+. Yeah, and then you have oxygen available, and that oxygen will reoxidize the diamond. So you have a method to store this carbon in the mantle. It's immobile. It will go into the mantle convective scheme, maybe go around for a couple of billion years. But when it comes into an upwelling, and you get to lower pressures, and the iron 3 rich phases break down, you produce a carbonatite melt. You do this on the perovskite breakdown to start with, and you do this finally on the majorite breakdown, which has also significant iron 3. And this is probably the deepest melts and the reason why you even melt so deep in the mantle. So, average metal-bearing deep mantle would freeze any carbonatite melt and all the juice that is contained in there. So also can immobilize all the goodies that we want in geochemistry. Okay. When we did this, we had to ask us the question what really happens, of course. So this is a conceptual model. I'm not claiming there would be a carbonatite dike. Almost certainly not. But you have a zone with a lot of carbonatite. You have a metal-bearing mantle. In between, you should get iron carbides. Yes? You do not have, there's not a single phase diagram published in which you would have graphite or diamond stable with iron metal. There's always a carbide in between. Okay, so we looked at these carbides. First, there is nothing at high pressure done except of the iron side. So this is 1050 degrees. We did the subsolidus diagram. On the nickel-rich side, you have diamond and nickel coexisting. Then you have a field with the 3 phases. But for normal nickel contents, you always have the iron carbide. We started this out on the basis of temperatures from previous studies. So we thought we'd do this at 1300 degrees because it was proposed that the solidus in this system is around 1400. And then we had to go down. We had to go down to 1100, 1200 degrees to not have melt. In other words, at 10 GPa, the oceanic geotherm is 1350 degrees C. And as you can easily see, this is far above this melting curve. Yeah? And these melts, they have only a few percent of carbon, 3.5 to 4.5% carbon. So you only need 400 ppm carbon to saturate 1 weight percent of melt. And that's close to what people think is the average carbon content. So the idea is that this lower mantle that doesn't have a metal, it actually has a iron-nickel carbon melt. So what we are proposing is that the deeper mantle has a very small melt fraction, probably less than 1% of this metal carbon melt. Okay, the very last thing, we go to the ultra-reduced mantle, we go to natural moissanite. Natural moissanite is found in serpentinides, in chromatides, in kimberlites, eclogites, and sometimes with diamond. It is always very light. Delta carbon 13 is minus 17 to minus 35, and sometimes it's associated with light diamonds. And what was proposed is that this is very reducing. That is correct. Maybe primordial ultra-reduced mantle, that I don't know. Certainly at high temperature, and that is as wrong as it can get. And lower mantle core boundary, because it cannot be high temperature, is the same. Why? We have done these experiments. We equilibrated silica carbide with olivine and autopyroxene. The resulting XMG in the olivine or in the autopyroxene is 0.998. Not 0.98, 0.998. So if you find silica carbide in the peridotite that only has olivine of that composition, it might be high temperature. Otherwise not. You can do then some calculations, and it is work that is also done with Anastasia Golubkova. We entered all of these carbides and the metal alloys into databases with the silicates, and we calculate this diagram. So here's CCO. This is olivine going to autopyroxene plus cementite. That's the equivalent of iron wüstite. So you get a field where cementite is stable. Then you get a ternary alloy, iron silica carbon melt. Then you get an iron silicide. And down here, you get silica carbide. If you look at the composition of the olivine, this is iron wüstite. This is where the cementite gets stable. You see the XMG of the olivine. It drops to almost 0 at this point. Okay, why does this help us? And this is my last slide, I think. If you take a grain of silica carbide of 1 millimeter, the reaction it will have with the olivine is this one. You need something like 5 to 6-fold diameter of olivine to react this grain away. You can take diffusion temperature, diffusivity of iron, magnesium, and olivine, which is very fast. So 1 centimeter diffusion at 1,000 degrees, you only need something like 100,000 years, and your silica carbide grain would be gone. Yes, it would react with the olivine simple through a diffusive reaction. So to preserve the silica carbide, you need to be below these temperatures. You need to be below 800 degrees. Oh, there's this. Sorry, that's the really last one. How do you even get to such low oxygen fugacities? You take any fluid that you want. I mean, it's low temperatures. We take a fluid. From the fluid, we precipitate. So this is carbon, hydrogen, oxygen. These are lines of constant oxygen fugacity. This line is the carbonate saturation surface. In this direction, you have carbonates. Yeah? You take this fluid, you precipitate, or you take CO2 out of the system through precipitation of carbonates. The fluid moves along this graphite saturation surface. Yeah? With this, you get up to here. And then you have to precipitate hydroxyl-bearing phases. You have to remove water. With water, you remove oxygen. And if you remove the CO2 and the H2O from the fluid, everything that is a bit more reduced just concentrates. So the fluids get automatically ultra-reduced. They're highly fractionated fluids, but they get ultra-reduced, and you can get to something like silica carbide saturation. But you only can do it at extremely low temperatures. So silica carbide forms at low temperatures. There's a number of ophiolites or mantle rocks that have silica carbide. It is low temperature and thus almost not possible to be very high pressure. Thank you.
Question?
Everybody happy? You because you would have high temperature. So you can have high pressure if you want, as long as you keep below 1,000 degrees. Yeah, I mean, there is silicate carbide with diamond, and in the roots you can have that, yeah, in the roots of the continents. But you cannot go anything like core mantle boundaries, so no way.
My question is, how low is low temperature? Actually, form silicate carbide during condensation, very low oxygen gas.
Some of the silicate carbide is found in serpentinites, but as far as I know, the serpentine, this XMG thing would apply to any phase. Any phase in equilibrium would have a very similar XMG, and I don't think these serpentines have so high XMGs. Yeah? So I'm not sure it's related to the serpentinization.
Okay, we need to liberate the room here for the next group. Thanks once again to all the speakers, and congratulations again to Max on the Dana medal. The festivities continue this afternoon in the poster session, so I'll see everybody there this afternoon in the posters.